Yes.
Okay, so dear colleagues, welcome you back to the Mathematical Game Theory, online Mathematical Game Theory seminar. And I hope that you enjoyed the summer or in the Southern Hemisphere, the winter very much. But we start working now, from now on. And our first speaker in this semester is Stephan Jagau, who is originally from Europe. He got his PhD from the Amsterdam School of Economics and then graduated from the Tinbergen Institute in the Mathematical Philosophy program in economics. And then he moved to California, and now he has a postdoctoral position in the Institute for Mathematical Behavioral Sciences at the University of California, Irvine. His main interest is behavioral and epistemics, which are related to our topics, a behavioral and epistemic topic of game theory. And his today talk is also something which is very related to this, the understanding transfinite elimination of non-best replies. Stephan, thank you for being here, and the screen is yours.
Alrighty, thank you all for zooming in, and thanks for the opportunity to present this here. As Miklos already said, this talks about understanding transfinite eliminations of non-best replies. Let me jump right into the talk. So what this is about in the end of the day is maybe one of the most basic ideas in epistemic game theory. Players should choose rationally given their beliefs about opponents' strategies. Players should believe that their opponents believe that their opponents choose rationally given their beliefs. Players should believe that their opponents believe that their opponents believe that their opponents choose rationally given their beliefs, and so on and so forth. That's one of the most basic requirements we can put on players' reasoning to make predictions in a game theoretic setting. And we would call this rational choice, and any number k of layers of this reasoning we call rationality, and up to k-fold belief in rationality. And how we normally study this is encapsulated in what's been called the fundamental theorem of epistemic game theory. For any k, a strategy survives k plus one-fold elimination of non-best replies if and only if it is rational given a belief hierarchy expressing up to k-fold belief in rationality. Here we have the procedure on the one hand, and the reasoning that's the behavior, and we have the reasoning that the behavior is consistent with if it survives that procedure. Now, in many popular applications, think of auction theory, think of industrial organizations. We look at games with infinitely many strategies because, for example, we don't, in an industrial organization setting, we don't want to commit to a say we look at quantity competition, we wouldn't want to commit to any quantity grid that firms choose when they engage in competition. So it's natural to move to an infinite grid in such cases. And then the question is, how would the fundamental theorem of game theory extend in those cases? Now, what we're all used to from most games that are nicely behaved, we would be looking at something like a compact strategy set for every player, continuous utility function. Then we have some one-to-one correspondence, not only in the finite case, which I already put out there earlier, but also in the infinite case. So if we go over countable steps of eliminating non-best replies, we would get to the terminal depth of reasoning, rationality, and common belief in rationality. Now, if we move out of this class of games, it gets more complicated. And I think that's first been observed in game theory by Lippmann's 1994 paper. somehow in some infinite games, in games with infinite strategy sets, we can keep eliminating after countably many steps. We can eliminate omega plus 1 steps, we can eliminate omega plus 2 steps, and so on and so forth. We can eliminate at least until the first uncountable ordinal, omega 1, and that's going to be kind of the practical limit for my talk. Why is it a practical limit for many games? Well, because after this, we cannot give an explicit example of a game where we would take more steps of eliminating non-best replies just as a consequence of the well-ordering theorem. We can't really think of an order that has more than countably many steps explicitly. Now, so then the question is, what do all those transfinite steps mean? Well, one intuitive answer could be the transfinite eliminations are just like the finite ones. So for each ordinal beyond omega, we have a reasoning depth, belief in up to alpha-fold belief in rationality that this transfinite step corresponds to. Well, but that seems a little troubling, because, well, then we have some infinite games where we get qualitatively different reasoning than in finite games. Well, but in a lot of applications, as I already mentioned, auction theory, industrial organization, what we do with the infinite games is we let them stand in for a whole class of large finite games. So we would like to be in a situation where we can be sure that what we qualitatively find in the infinite games is going to extend back to the finite games that they stand in for. So now we would be in the situation that we first have to figure out assumptions under which this stand-in of infinite strategy sets for finite strategy sets, for example, would tell us anything about the real life situation. Now, actually, it turns out to be, the situation turns out to be less problematic, because transfinite eliminations do not correspond to depths of reasoning. That's pretty much the message that I'm concerned with in this paper. That's also a message you find in other parts of the literature. But as you're going to see, I'm taking a slightly different approach, looking at belief spaces, and that's going to help us understand very nicely what the structure actually behind this result is, that transfinite eliminations do not correspond to depths of reasoning, and how, even though the finite correspondence of the finite fundamental theorem of game theory between steps of elimination and depths of reasoning, even though this doesn't extend to the infinite, we can still make sense of how this extension breaks down, and how, in some sense, in a more complicated sense, it's still a reasonable extension of the finite result. So let me, so what we're going to find in particular is that common belief in rationality is equivalent to countable layers of belief in rationality in any game. What's different, though, is that non-best replies and information loss caused by this way of describing the behavior that's consistent with common belief in rationality causes these transfinite eliminations. And that's really where I think a belief-based view at this problem helps, because it helps us understand the distinction between the tools and the subject matter of the analysis, so to say. Let me illustrate, to start, let me illustrate what's going on with an introductory example. I think a lot of you might have seen this. This is from the Duffenberg and Stegemann paper 2002 about iterated strict dominance. So we're looking at a two-player game. Those two players play a standard Cournot game. So they choose their quantities to maximize this standard profit function. And we have a third player, though, and that player, as it were, is going to bet on whether the Cournot equilibrium results. So he has two strategies, and one strategy is going to be preferred if and only if he's sure or to the degree that he believes the other two guys are going to settle on the Cournot equilibrium quantities. And for any other situations, he's going to prefer his alternative strategy. Now, it's relatively easy to check that that we need omega plus 1 steps of elimination of non-best replies in this game to get to get to the smallest reduction, so to say. How can we see that? Well, omega steps in a standard Cournot game are going to be necessary to get to the 1-3-1-3 Cournot equilibrium between the two players. Well, and then if the third player is sure that they're going to settle on the 1-3-1-3 quantities, then he's also going to strictly prefer his choice or his strategy E to his strategy N. So then we can ask, does that mean we can rationalize N under up to k-fold belief in rationality for all finite k, the strategy that survived the omega steps, if the finite version of the fundamental theorem of game theory extends just straightforwardly to the infinite? We should expect that this would be possible, but actually we can't. Now, why is that true? Well, it becomes pretty apparent if we do a slightly more complicated analysis and actually try to drag along explicitly the first order beliefs for player 3 at different reasoning depths. And we can see, well, we have a law of motion for the quantity intervals that the two other players can choose, and that player 3 can then consider in his first order belief that pretty much follows from solving the Cournot game. And what we see here is that as k increases, he has to choose from these ever smaller intervals. And if we go over these intervals that he can choose his first order belief on, if we look at the limit of these intervals over countably many k, then we already get to the belief in the Cournot equilibrium with probability 1. And then E is uniquely rational. So what's going on? Well, there is actually no belief that would rationalize the choice N under countably many layers of belief in rationality. And I should add, there's no fixed belief. So what's going on really is what it means that it survives the countable layers of elimination of non-best replies. This choice N is that there is some belief for every layer. But if we actually look at what this first order belief can be, it turns out that it has to change at every step. And we can't find a fixed belief that's going to rationalize the choice under all layers of beliefs. So we can conclude at this point that the choice is actually not consistent with rationality and common belief in rationality. So the way it looks, the game features countably many layers of strategic reasoning, even though there's omega plus 1 steps of elimination of non-best replies. Well, and this turns out to be true more generally. And what I'm going to do next is I'm going to walk you through the core results of the paper. That's going to explain a little more how we understand the additional transfinite steps. Here we kind of see how it works for one additional step. How's it going to work for any number of additional transfinite steps? And in the end, I'm going to give you a second example where we see that at play. So let's look at the let's look at my core results in the paper. So let me first give you some definitions of what I'm working with. Only working with static games here, and by a static game I mean I have a countable set of players, I have a separable set of strategies for each player, and I have a set of belief hierarchies for each player expressing coherency and common belief in coherency, and I have a measurable utility function that's also bounded from the product set of strategies and first order beliefs. couple notes here. So this set of belief hierarchies, I explicitly consider here as part of the game to start from different layers of rationality as properties of strategy belief hierarchy tuples, as we're going to see in a second. And that really bears out this idea of distinguishing the reasoning concept that we're interested in from the procedural characterization we use for it. For example, common belief in rationality on the one hand, elimination of non-best replies on the other hand. The way this is constructed is pretty much in the spirit of Brandenburger and Dekel, but I look at a more general setup here. Turns out that you can do something similar for the more general setup under basically no assumptions about what the strategy set looks like. That's what Heifetz and Zamet show in their 1998 and 1999 papers. What's going on here in principle is that you have to be more careful about how you define coherency and common belief in coherency for all this to go through. The only assumption I make on top of this is that I need a separable set of strategies, and that's really to be able to measure the output of my utility maximization problem.
Can I ask a question here?
Yes.
In your definition of game, the payoffs depend on beliefs.
Yes.
Is that a construction you can build on a more conventional definition of game where payoffs depend only on actions?
Well, I think it's I mean, in most cases, this is equivalent as soon as I have a function that's as soon as I have some kind of expected utility theorem in the back, I would be able to replace the function u that I use here by a small u that goes from strategies and opponent strategies to the real numbers. Yeah, so what I'm pretty much doing here is I'm trying to abstract from expected utility and other such considerations. But yeah, but for most examples, as you're going to see, it's not going to matter. What does matter is the difference between non-best replies and iterated strict dominance. You can also get similar results for iterated strict dominance, as I show in my paper. But then you get some additional complications that you wouldn't get with non-best replies. Yeah, but actually then we need to make even stronger assumptions, because even if we have something that's linear here, we wouldn't be guaranteed to have Peirce's lemma yet, which we need for iterated strict dominance. That's kind of how I ended up with this. Yeah, just like the smallest set of assumptions for which non-best replies work. So I'm not sure, I mean, if you look at it from a decision theoretic perspective, I'm not sure if it's maybe too general to be sensible, but I guess also the goal here is to find very weak assumptions under which we can understand how these transfinite eliminations fit into the goal of going from a finite game to an infinite game. And yeah, here I'm really driven by the consideration. If we look at all those finite games, we don't really yet know what the infinite game that stands in for them is. So if we're a little more general than necessary, that's only gonna help us be sure that this will work out in most cases we actually care about.
Can I?
Sorry, Stephan. Yes,
go ahead. And try to answer Eagle's question differently. BI is simply a state of the world. Although in the setup there are no states of the world, because every player has a different set of states. But if you do it properly, then you have a set of states of the world, and then BI simply is the state of the world.
Mm-hmm.
And then it becomes a games with Harsanyi games, a simple Harsanyi game.
Yeah, that's true. That's a good addition maybe to what I was saying. So in some way, this is very similar to looking at an Aumann model of a game or something, where I'm not using knowledge spaces here, and that would be a little different. I'm going to say something about that at the end. But the goal here is really also of drawing in those belief hierarchies, of having a full description of what's going on in players' mind as part of the model of the game.
That's true in every Hassani game. You have full hierarchies that can be constructed from the game, from the description of the game. So the idea to start with hierarchies is a little bit bizarre, but okay, let's go on and see.
Alrighty, let's see.
May I ask a question, Stephan,
yes.
on the previous slide, just to understand the last line that's separable SI. This is in order to make the set of maximizers a measurable set. Is that what you?
Yes.
And does it guarantee that this set is non-empty somewhere? It's not, right?
No, and that's
okay. It's just about measurability.
Yeah.
Okay.
Let me get to that in a second. Actually, I'm going to
thank you.
about that on the next
what
slide.
do you mean separable? By the way, I don't know. What is separable SI?
Well, in a topological sense. So what I
so
I
SI
wanna,
is a topological space.
Yes.
Okay.
So what I get out of this is I have a countable dense subset.
Yeah, I know. Okay, so the topological separability, yes. Okay.
And Stephan, then what do you mean by data of S minus I? So you consider all on the Borel sets, all probability measures over the Borel sets of S minus I, or just some probability measures, the regular ones, or?
Yeah.
Because you mentioned Heifetz and Summit later, but in those papers, no topology at all. So.
Yeah.
Well, so what I'm doing is, I use really this construction from Heifetz and Lamet. I think if you look at this, well, okay, at the bottom, it's not really specified what you put in there. So there I put in the Borel sigma field, and then going on from there, what you would get is the Borel cylinders over the probability measures.
Okay, so you consider all probability measures on the Borel sets. Okay, thank you.
All righty. Okay, so let's go on. So that's what the games that I consider look like. Let's look at what rationality in my context looks like. So what I'm doing here, and that's why I really had the belief hierarchies in the definition of the game on the previous slide, is I want to define rationality and belief in rationality as a property of strategy belief hierarchy tuples. That way we can be sure that all the information that the reasoning concept gives us is actually in its definition. So for rationality, that means I have a strategy SI, I have a first order belief BI1, but in the end, I'm going to talk about the belief hierarchy and the strategy here. And I'm going to say the strategy is rational given this belief hierarchy if BI induces a first order belief such that the strategy is optimal for that first order belief. And now, we can just nicely go on and iterate that concept by saying, okay, we're looking at the tuples that survived the previous step, and the belief hierarchy has to be drawn from the probability measures over all opponents tuples that survived the previous step. Now, and what I find nice about this, and we're going to see that at work in an example, is that here we're explicitly keeping track of all the constraints that the concept imposes. We have constraints on first order beliefs already after the first step, on second order beliefs after the second step, and so on and so forth. And for any K, I'm going to say that a strategy is rationalized by a belief hierarchy under up to K-fold belief in rationality if it's in the K+1 reduction. Sorry, I just got a little confused there. Must be the early time. Okay, so in the same way, we can also go on and define common belief in rationality. Strategy is rationalized by a belief hierarchy under common belief in rationality if it is in the countable intersection of all these reductions. And yeah, here's my first result, so to say, but it's pretty banal. If you look at this, it's always going to be best response kind of set. It's going to have a fixed point property. So from there, it's pretty easy to show that independent of what game we're looking at, we can keep iterating this and it's not going to change anymore. So that's what I call terminality of common belief in rationality. If we define common belief in rationality in this way, at least at this point here, we're not going to have any transfinite steps that are of any use to us. So it must come from somewhere else. And to figure out where these transfinite steps come from, we now can contrast this with elimination of non-best replies. How do I define this? Here's k-fold elimination of non-best replies for finite k, first of all. So what I'm saying here is also pretty standard, I guess, just accounting for the fact that my utility function doesn't need to be expected utility. So I say non-best replies first step, any strategy such that there's a first order belief that makes this strategy optimal. And then I go on and say, I look at every first order belief that distributes over the previous reduction, and then I impose the rationality requirement again. And that kind of weaves in with a question about whether the sets can be empty earlier. Here's actually where I account for this possibility a little bit. It's two ways of, or two common ways one could define k-fold elimination of non-best replies. Either we say we look at all the beliefs that distribute over the survivors of the last step, and we still keep comparing dominance relationships among all strategies available to a player, or also just the surviving strategies. Well, I'm doing all strategies here, and that's really to deal with the possibility that any of those finite orders of non-best replies might already be empty. Why could that happen? Well, if your utility function is not continuous, you're not only worried about strategies such that there's no belief that makes the strategies optimal, but you also got to start worrying about beliefs such that there's no optimal strategy. And well, one way to deal with those is to say, kind of in my reasoning here at least, is looking at a property of strategy belief tuple. So we don't really care whether the problem comes from the belief or the strategy. If there's no rational strategy for a belief, we also throw out that tuple. And that's going to work as long as we eliminate among all strategies, so also previously eliminated ones at every step. And yeah, and what can then happen is at any step of this elimination procedure, we might come out with the empty set, but then my results still apply in this specific case. So as long as if we get to something that's transfinite and non-empty, then what I'm talking about is still going to be true for that case, even though it might be empty in certain situations, what comes out of the procedure.
In your definition of NBR, you seem to eliminate a strategy that gives a higher payoff. Is that what you mean to say?
Do I do that? I think I'm saying I'm taking all the strategies such that there's a belief that this strategy is at least as good as every other strategy that's available. So that's how I mean it either way.
So what do you mean by negation? Not. What is not here?
what knot are you talking about? Oh, in the name of the, yeah. So that's maybe not so nice here about the slide. Yeah, I should give this a different name. That's good that you pointed out. That was mainly based on the fact that belief in rationality is already BR, and I had to find a name here. Probably I should use some CI of K or something. Yeah, so the name here is not.
So it means possibly best reply. So it's possible.
Yeah, so those are all the strategies that survive the procedure, not the ones that are thrown out. Notwithstanding the N. Yeah, I'm sorry about that. So with these definitions in place, we can go on to the finite fundamental theorem of epistemic game theory. And yeah, that one goes through independent of my or under these very weak assumptions, unchanged for any static game, any player I, any strategy Si, and any finite K. There exists a belief hierarchy Bi that rationalizes Si under up to K-fold belief in rationality if the strategy is in the K+1th reduction. So let's look at the more interesting case, omega-fold and transfinite versions of eliminating non-best replies. So the omega-fold version is just going to be the countable intersection of what I defined on the last slide just. How does transfinite elimination work? Well, we can distinguish between successor ordinals and limit ordinals, and then we kind of get the definitions we got for the finite and the countable case back, right? For every successor ordinal, we look at first order beliefs that are distributing over the reductions for the previous ordinal, and then we impose the rationality constraint given strategies matched with those first order beliefs. And if we go to a limit ordinal, we intersect over all the sets that we have so far. So
sorry, Stephan. So in this case, when you take somehow these transfinite steps. So you, at the beginning, you had a sigma field, and then these MBR I's for finite case are events, right? But when you take the infinite intersection, those are not events anymore. So then when you take the subspace and you say that, okay, so I mean that originally we have events, we understand what those events mean. And then you take the iterations, and for every finite sub still we can interpret what's going on, what is the meaning of the event we get, even for omega. But when we go for omega 2 or something, then I don't see that what kind of the set which we get is out of the original sigma algebra or sigma field. So how do you interpret this thing?
Well, I mean, first of all, I wasn't aware of this, so that's something I should look at, and maybe we can talk about that more after the talk. But I mean, there could be two ways of dealing with that. I mean, well, first of all, one thing that comes out of this is that there's no set of belief hierarchies that would correspond to that reasoning. So I think in some sense, it's maybe not surprising that under certain conditions that doesn't work out anymore. As long as the iteration over all ordinals gets us back to a set that we can interpret as strategies times probability measures, I think that would still work. Well, yeah, that's as much as I can say. I think that could be something that could be true, and then my results go through without any change, or otherwise I might have to use stronger assumptions at this point about the strategy set. And that's part of what I wanted to find out with giving this.
Because if you assume that you have compact regularity at the beginning for the beliefs, then because those only the compact sets does matter. Perhaps, you know, and you can arbitrary intersection of complex sets. So perhaps then you get something, but I'm not sure. But so what I would like to say that even when you define the NBR alpha for high ordinals, perhaps it's a problem, not?
Yeah.
Well, not for the result, even for the definition, not?
Yes, I mean, it's something that I was wondering about before the talk already, but I didn't have a good answer. So that's a good hint. Yeah, I mean, for any of my examples, it doesn't really matter. So part of what I'm trying to do is find the most general assumptions under which everything goes through. Definitely everything goes through if we go back to something like a Polish space, like in the Brandenburger and Dekel setup. But I have a feeling that you can relax this a little bit. So that's part of what I'm trying to figure out. Yeah, so I agree. I mean, I think the question at this point is, what are the weakest assumptions under which this can be defined? And then a lot of stuff could happen with those sets, because in the end, as I'm going to argue, we're only going to be interested in the final outcome. But yeah, the definition should be sound. Okay, either way, so maybe preliminarily we can think of the strategy set as a polar space. In case that doesn't go through, then I'm sure it's going to go through, but maybe it's under weaker assumptions possible too. Either way, we can now look at two versions of this infinite fundamental theorem of epistemic game theory. First, we can look at the general version and say, well, there exists a belief hierarchy that rationalizes SI under common belief in rationality, if and only if it survives all these ordinal steps of non-best reply elimination. And then we can look at the more usual case and say, well, if we have something that's compact Hausdorff and we have a utility function that's continuous in the weak topology, then we know that also with the non-best replies, iterating beyond countably many steps is not going to change our result. So it really breaks up into those two components. And that's also not completely new, but what's nice about looking at it in this belief-based way is that now we can look at the first bullet point and really try to understand what's going on in this case. What if those requirements don't embody other layers of reasoning, what do they embody then? Might be an interesting question. And that's what we can look at more closely with this belief hierarchy based definition or strategy belief hierarchy tuple based definition of rationality and common belief in rationality. But what we already see is those transfinite eliminations are unrelated to reasoning depth. Common belief in rationality is terminal in every game. Each strategy that does not survive transfinite non-best replies consequently must be inconsistent with belief in rationality of order k for some finite k. And we saw that nicely in the Cournot example for every fixed first order belief. If we ramp up the k high enough while keeping it finite, that first order belief is going to fall out. Can just point to a different one at each step, but that one's going to change over the course of the procedure. So we come out with nothing at the end. Yeah, so what do these transfinite eliminations correspond to then? Well, we can call this information loss, right? The non-best reply procedure selects strategies that are consistent with belief in rationality. And belief in rationality of order k is a property of strategy belief hierarchy tuples. So in general, what is consistent with up to k-fold belief in rationality for all k in terms of behavior is not necessary. That something is consistent with up to k-fold belief in rationality for all k does not necessarily imply that it's consistent with common belief in rationality, and that's really the problem. Here's a little figure that also illustrates this, where I color the kind of information that the reasoning concept and the elimination procedure would keep track of. As I already mentioned before, well, what happens with belief in rationality is the belief, the order of beliefs that is constrained just goes up and up over the course of the procedure, right? First we ask, is the strategy rational for the belief hierarchy? Then we're gonna get constraints on the strategy and the first order belief it's matched with. Then we're gonna ask, is it also rational if we believe in the opponent's rationality? And then we're going to get constraints not only on the first, but on the second order belief, and so on and so forth. And yeah, meanwhile, with non-best replies, we're looking only at the strategy information in blue here. So that's really the information that's lost here. Here, to wrap up the talk, what I'm going to do is I'm going to illustrate this with an example. This is from Lippmann's paper. Not going to expect you to understand immediately what this matrix is doing. What you might note is every player chooses from two countable sets of strategies. So we have these two countable components here, and that's what's going to bring the transfinite eliminations in. Because what happens here is for every finite order k, the D strategies, the dk plus 1 strategy is going to be eliminated at a finite order. And the strategy D1 is only going to be eliminated after eliminating all the k's with an index larger or equal than 2. And so that's going to happen after countably many steps. And then we can keep on eliminating through the A strategies. Only after 2 omega steps, we're going to come out with the strategy A1 as the sole survivor. So by my earlier results, all those steps omega to 2 omega of non-best replies are also jointly equivalent to the omega step of belief in rationality here. So how can this work? I'm going to illustrate how this is going to work right now. This is going to give us an idea of what these transfinite elimination steps really mean if they don't mean additional layers of rationality. So how are all these choices, D1, A2, A3, and so forth, eliminated at reasoning depth omega? Just look at the constraints that belief in rationality puts on behavior and beliefs. This way we can see that, well, at the omega step, we know that all the DKs with an index larger than 2 have been eliminated. But then what's also true under common belief in rationality at reasoning step omega, all strategy belief hierarchy tuples with a first order belief that believes in those D index larger than 2 strategies have also been eliminated. Well, but that must include all strategy belief hierarchy combinations that deem the strategy D1 possible, because we know it's only optimal if those D2 strategies are available for the first order belief. But then we can go on. Well, it's also going to be true that any second order belief that entertains a first order belief that deems these D larger than 2, index larger than 2 strategies possible, those are also eliminated. And that includes all strategy belief hierarchy tuples that deem the choice, that involve the choice A2 as the strategy, and so on and so forth. And well, if we iterate this reasoning, what we can see is at any level of the belief hierarchy, we can't deem those D strategies that were eliminated by non-best replies until step omega possible anymore. But then that's gonna spill over to all orders of beliefs, and going back, as it were, all constraints fall back and are going to lead us to conclude that any belief hierarchy that deems possible those choices at some level is eliminated, and those are all belief hierarchies except for the one where we put full probability on the choice A1 at every level. And that's going to be a belief hierarchy for which A1 is uniquely optimal. So what's really happening here is we have some kind of jam because of how many strategies we're looking at. And what's going to start happening is constraints coming from the higher order beliefs are going to fold back, as it were, and are going to cause additional eliminations all at once at the omega step of the reasoning. And that's really why we get the transfinite elimination steps here, and how we can understand these transfinite elimination steps really as a second hierarchy that talks about what order of belief information do we have to look at to figure out that this choice or this strategy is also not going to survive the step from finite orders of belief in rationality to common belief in rationality. So are we allowed to use any information, we can ask then? Well, something we've seen here is as we go up in the belief hierarchy, or as we go up in the depth of belief in rationality, we get more and more constraints on finite orders of beliefs. That's really in virtue of the utility function going from choices and first order beliefs. What we can do is we could define a procedure that only keeps track of these constraints that we know can be imposed up to this point on the strategy belief hierarchy tuple. We call this elimination of non-best replies and supporting beliefs. So how that would work is we start with strategy first order belief tuples such that the strategy is optimal for that first order belief. Then once this is defined, we go to strategy second order belief tuples, say the second order belief distributes over the previous reduction, and the strategy is optimal for that second order belief, and so on and so forth. And then when we go to step omega, what we're going to do is we're going to just extend all the finite layers in an arbitrary way. We know that on the rest of the belief hierarchy, because the utility function depends on strategies in first order beliefs, there can't be any more constraints. Now we have countably many sets of strategy belief hierarchy tuples. We intersect over these and we get our strategy belief hierarchy tuples expressing belief in common belief in rationality back. So in a way, this is really a complicated rewriting of the definition, and that's also kind of what comes out in the proof, that this characterizes, if you marginalize it again, characterizes the strategies that are consistent with common belief in rationality. But I think what's nice about it is that it really captures what all the constraints that we pick up look like, and what the fallback is in terms of the most complicated procedure where we don't use all the information, but where we can still work with any game and know that we're not going to run into those transfinite eliminations. So what turns out here, and you might already think that because it goes back to the definition, as I said, is that this always works in countably many steps. Okay, so that pretty much sums up my results. Just some extensions and open questions. So for psychological games, that kind of goes back to the slide I just showed you. You can make this a little more general. As I already said, this very general procedure is based on what the utility function, what space the players care about based on how we define the utility function. If we go from choices in first order beliefs to choices in higher order beliefs, this result is not gonna apply anymore, just because at the basic finite level already a procedure would fail to characterize consistency with belief in rationality. So what we can do here is we can increase the order, and then we really come in a way we have a nice result, because if we go from first order beliefs all the way to belief hierarchies, we're also slowly going to approach a point where only the definition that I showed you at the very beginning would ever be sufficient to bring out all the constraints that matter for finding the behaviors consistent with a constant. Now, as I already said, what we could also do is we can look at iterated strict dominance instead of non-best replies. Now for that, we would need stronger assumptions up to the point that we have expected utility, and then that we have Peirce's lemma. And well, something that's interesting there, which I don't consider in the paper, but we might discuss this after the talk. If Peirce's lemma fails, can still be the case that strict dominance gets everything right, but we might have the weird situation that non-best replies and strict dominance give us the same prediction in terms of behavior, but stuff gets eliminated at different points of the procedures. So in particular, strategies that get eliminated very early on with non-best replies might be moved all the way behind countably many steps with iterated strict dominance, at least in the examples I've been looking at. Now, a more general question that I also want to mention is the knowledge versus belief spaces question. There's a lot of papers out there, Lippmann, Bach and Cabeza. There's also a note by Samet that consider state spaces and a knowledge operator. And then results can differ, at least based on what's going on in Bach and Cabeza. But apparently what's going on there is the partition structure that you work with needs to be sufficiently sparse to get qualitatively different results. So if you use something, some situation where players consider very little states, it can suddenly happen that common belief in rationality can be refined. Now it's not really clear how you would make a straightforward comparison between knowledge and belief spaces. One way we could do it is we replace the knowledge operator with a belief operator, use some infinitary logic like in Meyer, extending Heifetz and Mongin. And then I could imagine that discrepancies might disappear, but that's really just speculation. Just a general conclusion, and that's what I'm going to end with. As we saw here, the whole question around transfinite elimination is really a question of tools versus subject matter, you could say. We want to figure out which behaviors are consistent with this reasoning, belief in rationality. Normally we use this tool of non-best replies to describe those behaviors. And yeah, as with any tool, that makes our job a little easier with some kind of workaround, like here, just looking at the strategy-based information. We just have to be careful when we use it. And once we take this into account, infinite games look maybe more similar to finite games than we would think based on different approaches to the problem. Alrighty, that's it. Thank you for your time. I'm happy to hear any questions or comments. I'm gonna bring out a draft of this paper on my page pretty soon after this talk. So you can find it there probably this week, or otherwise you can also write to my email here and I'm happy to send you a draft if you're interested. Thank you.
Thank you, Stephan. Questions, remarks? I see that Iga is still thinking, so I take the first question.
I have a question,
okay,
but
great.
I'm not sure how applicable this is. I just remember from a long time ago, you are a member of the Epicenter in Maastricht, and I remember a talk by Andres Perea, which was about the elimination procedure, whether the order in which you are eliminating members of a set matters for the final outcome. So in this case, since you eliminate all strategies that cannot act as a best reply, this is perhaps not as important, but I just wonder what happens to this if if you look at more general elimination procedures, and we do not kick out all the non-best replies in one go, but in smaller proportions.
Yeah, so based on, I mean, that's something that I've been trying to abstract from as possible in this paper, because what I realized when I was working on this is that it's really different things that cause this. I would say apart from this strict dominance, non-best reply situation I was just talking about, I would say the most common case of this happening is the non-existence of optimal beliefs. So that's why I'm using the version where you keep eliminating over all strategies and not only surviving ones. And I think there's this paper by Vigrom and Roberts that shows that this works in very general. I think even more general than what I'm using here, because they don't care about whether there's a belief hierarchy or like a set of beliefs that rationalizes something. They only work with iterated strict dominance. Yeah, but that's really what's going on, I would say. So that's, as soon as you drop this way of formulating the procedure, as soon as you allow yourself not to compare to all strategies, and probably
things like that,
as you eliminate a little slower, even under this very general formulation, you would have to reckon with order effects. And another thing that turns out to be true, that's maybe been considered less, is that really if you move from non-best replies to iterated strict dominance, you can get similar order effects. And then it's going to be completely independent of whether you eliminate in the fastest way possible. And it's not going to matter for the final results, just going to matter for the order. So this might only concern us if we really care about what level of rationality some choice or some strategy is consistent with.
Thank you, Stephan.
Stephan, of course, I'm thinking about that. What is the role of the definition of game in your results? So what if you generalize the definition of games to the case when you don't have a utility function, but you have only preferences over the strategies and the beliefs versus the beliefs? Then you cannot. Because of the utility function, you get to the real numbers, and you use the structure of the real numbers in the reasoning somehow. So what do you think? Could you get the very same results? What is your intuition if you relax the notion of games in the way as I mentioned, or you say you don't think that it is important? I mean, the definition of game is important in your results.
Well, I mean, specifically the question of whether there's a utility representation, right? Is what you're aiming for. Well, I think it's going to matter what assumptions about the preferences that are necessary for a utility function are met and which aren't. I mean, with very basic assumptions like that there's going to be no local preference cycle at any belief, I imagine that you might get problems getting through with the same result. But that's not going to be enough to just not having a local cycle. I think it's not going to be enough to give you a utility function. So yeah, so maybe it's going to depend on the assumptions, but I could imagine that if you make your assumptions weak enough about those preferences up to the point where there's no representation anymore, there are certain sets of assumptions where different things might happen than here. Yeah. I mean, maybe the knowledge space kind of results give an idea here. If we arbitrarily restrict players not to consider certain states possible, then we can also break the result that common belief in rationality can't be refined. So then my results would break down. And I could imagine that if you give yourself a lot of liberty regarding what the ranking of strategies is at each possible state that the player considers, you could find a way of mapping those cases just directly into this kind of setup.
So I'm not sure that you could hear my question, Stephan. Could you?
No.
No, sorry, then I'm lost. So my question is that what is the role of the definition of games in your results? So what do you think if you generalize the notion in the sense that you don't have utility function, but only you have preferences over the strategies and the first order beliefs over the other strategy profiles over and the truncated strategy profiles of the others. What is your feeling? Could you get something different, or practically does it matter and you could get the very same results?
Yeah, so I mean, I think, yeah, you could probably just take these results, like for example, from the Bach and Cabeza paper, and map the situation where you just don't consider certain states of the world possible just directly into a situation where you give your utility a lot of not your utility but your preferences a lot of liberty to just not react to certain changes in the states. And then I could imagine that you could replicate that situation there. So my feeling would be that you can find examples where, based on preferences without a utility representation, you can break the result that common belief in rationality can't be refined, and then that's pretty much what all my results here depend on, I would say.
Okay, thank you. Further questions or remarks? I don't see any. Then thank you again.
Thank you.